Alright, hell yeah. So we have a statics problem that has kind of difficult geometry. And this is kind of the quick solution. We're going to go through it. We're not going to use any angles at all. We're just going to use Pythagorean theorem. One of my axioms is if you know two things about a triangle, you can know all three things. So in this situation, we know this distance x, and that's going to be that x. We know this distance is 10 meters. We have this weight on a pulley, and then we have another weight. This weight is fixed at 8 meters, so this weight can't slide back and forth up this rope. We just want to know when the system's in equilibrium. And so, cool. And so we got all three parts of this triangle in terms of this value x. We're going to come over here to this triangle. We only know one thing about it, but oh yeah, it's connected to this, so we now know two things about this triangle. So now we know everything about it. We just use Pythagorean's theorem. This squared plus this squared equals, or the square root of this squared plus this squared equals this. So, and then I just factored this. This squared is going to be 10 squared plus x squared minus 20x. So we have a minus x squared here, cancels the positive x, and then we pick up a 10 squared. So you can kind of do that one on your own. How did we get this again? To get, if I know the hypotenuse and one of the sides, I take this hypotenuse squared minus the side squared. Square root that, that's going to be this side. When I know both sides, it's just this squared. That's going to be the 8 squared minus x squared, and then add it to this. But since this is a minus x squared, and then we're going to pick up a positive x squared, after squaring this, those goes away. We do have this 10 squared, and then the middle term, that negative 20x. All right, so we know all three things about that triangle. Now for equilibrium, we have the weight down is going to equal the tension in this rope, but only the vertical component. So this is why we did all that with the Pythagorean theorem. The vertical component, the percentage of that tension, is just the vertical distance here divided by the hypotenuse. So that's going to be square root 8 squared minus x squared divided by 8, multiplied by the tension AB. And then we're going to add it. We have another tension over here. This tension in the rope due to a pulley is just W. Cool. And the percentage of that W in the vertical direction is going to be this distance divided by this hypotenuse. So that's what we have right there. So that's our first equation. The second equation says that the horizontal components of these two tensions are like fighting each other. And they also have to be balanced. If one is bigger than the other, this point's going to be moving. But we know it's a static situation where it's not. So we say the horizontal component's going to be x divided by the hypotenuse. So that's where we get that. The percentage, the fractional percentage, I just like to think of it as a percent. But of this tension in this horizontal direction is going to be this distance divided by the hypotenuse. Even though the tension is going to be in pounds and these distances are unrelated to the actual tension, but they're in the direction that the tension would be. So we're going over x, this distance, this compared to the distance of the hypotenuse, it's a percentage. We say this hypotenuse is like 100%. Well, it looks like that's going to be about 80%, you know, the way the picture is drawn. And so to get that percentage in the horizontal direction, we take that horizontal distance, x divided by the hypotenuse. So x divided by 8 times that tension is going to be the horizontal component of that tension. The horizontal component of this is going to be, well, we know the tension's W, and then it's going to be 10 minus x divided by the hypotenuse. So there's our second equation. And now we're just ready to rock and roll. We're going to solve this one for that tension, so get everything to the other side. And now we have this tension AB is equal to all this. Now we can shove this into there. I kind of said 1 into 2, but you know, we're just kind of combining. These are our two equations. We're putting them together. So once we solve for this TAB, shove it into here. So that's what I did. Now when I do that, I'm going to have, up top, I'm going to have 8 times 10 minus x times this square root 8 squared minus x squared. Down below I'm going to have 8x times the square root of that. So that's what we have. So we have this 8, 10 minus x multiplied by that Downstairs I'm going to have yeah, 8x square root all that. Cool. And then I have this w term, so I'm substituting this into there. This goes away, we pick up a w and all these extra terms. This side we already have a w, stays the same. All right, and then that's going to equal w. I just flipped the equation. Started with this, added this, and then that's equal to w. We have a w everywhere, so I'm just going to factor that out. This side becomes 1. And now we have to add these fractions. I guess I was just ready to be like, whoa, I have an 8x square root all that. I just have a square root all this downstairs. I need to make the denominators the same, so I needed an 8x. But I was just realizing, oh, I can just factor out this 8 right away. And then all I need to do is pick up an x. So I just need to put an x right there. And now we're going to add these straight up. But I can also see that I have this term in both sides. So I'm going to factor that out. I'm going to say square root 8 squared minus x, parentheses, 10 minus x plus, and then over here, but I did pick up, I guess you really can't see it very well. I do have an x downstairs square root. I need an x downstairs here. When I put an x downstairs, I gain an x upstairs. Cool, now my denominators are the same. So now when I add this upstairs, I'm still going to factor out the square root 8 squared minus x squared. I'm going to have that 10 minus x plus x. So cool, those two terms drop, and I'm left with 10 square root x squared minus x squared. Cool, up top. But I guess to finish this equation, we just added the top terms, and we made the denominators the same, so it's just going to be divided by that denominator. And that's going to equal 1. Now I can move all this upstairs to the other side. So again, we have 10 square root 8 squared minus x squared is equal to, this is now upstairs. Hell yeah. Now, I really want to get rid of this square root, so I have to get this inside the square root. I just say 10 is 10 squared square root. Once I get this as a square root multiplied by a product of a square root, hell, I can bring it inside. So, and the same thing here, just square it, but take the square root of its square. That's the same thing as x. Just like 10 squared is 100, square root is 10. These are synonymous. I didn't change anything, but I got this with a square root over its head, and now I can product it in. You don't add it in. You know, if I have the square root of 10 squared multiplied by the square root of all this, I can get it inside, but I have to multiply the 10 squared by this. Okay, hell yeah. Just like I have to multiply this x squared by all that. Okay, hell yeah. But now I can square both sides. The square root goes away. Cool. So I have this. Now I can factor, like FOIL these through, and I'm going to get 8 squared times 10 squared minus 10 squared x squared is equal to, I'm going to have 8 squared x squared plus 10 squared x squared minus 20x to the cubed. Cool. And then I'm just going to get everything to one side. I'm going to start out with the negative 20x cubed. Now I'm going to start with the x squareds. There's one, and then I pick up, I'm going to add that over here. So I'm going to have an 8, a 10, and adding another 10. We have 8 squared plus 10 squared plus 10 squared. These are my x squared terms. Now, those are my x squared terms, and I'm just left with the constant. Subtract it to the other side, and booyah. And I just threw this into my calculator. So we have negative 20x cubed plus 8 squared plus 10 squared plus 10 squared to the x squared minus 8 squared times 10 squared. So we're going to graph that. This is the equation that we get. It's a really large, I had to scale everything up. Negative x goes from negative 50 to 50. Y goes negative 10 to the 4 to positive 10 to the 4. Zoom 6. Just kind of, our x has to be somewhere between 0 and 10. So it's going to, as long as my calculator don't blow up. Alright, let's try it again. Alright, booyah. And so, our positive root, and we're going to get a value on that. 7.4. Going to get a 0, left bound, right bound, and get a value. And heck yeah, we get x is 7.48. meters. And so, booyah. So that was kind of just the fast solution to go through here. I think it's always good to do that. So let's get on with the video. We go over a lot of aspects of how to do that ratio. So without further ado. Alright, hell yeah, we have engineering, mechanics, statics, and this author is Pathagorean. And booyah. This one's hard to find with a PDF for free online. But anyway, we got a question from there. Most of these are in the Hibbler. They're very similar. And this is a starred problem. So a viewer wanted a geometry using trigonometry that was more difficult. You know what I mean? Maybe you had to, it wasn't so straightforward. So this is the problem that we're going to do. And we're going to take a look at the layout. So we have a pulley right here. And the first thing that we need to know is that, like, a pulley or a rope going around the pulley has the same tension in this side as the same tension in this side. So if we're asking, like, hey, this weight, and you can just imagine, you know, to simplify these, just pretend the weight is like all right there. Sometimes it gets a little bit headachy of just like, well, I guess we have a point here, and this point is getting pulled this way, and then downward. But if you just think of the weight right there, then you're just like, hell yeah, this weight is being pulled this way, and it's being pulled that way. And the tension in this rope this way is just equal to this weight. So this weight has a mass, and that weight is just mg. Sweet. So the tension in this rope is mg, this mass times gravity, or just this w weight. And we're saying that these two weights are identical. So we got that going. Now the other part of this problem that might not be too obvious is that this point is a rigid fixed point on this rope. This is not a pulley. And that kind of got me, two aspects of this that kind of got me, I had to think about this for a little while. Is that if this was a pulley, then, like, so that's why I pulled out this drawing right here. So, like, hey, it looks like those are pulleys, but for whatever reason, maybe this is actually a motor that's able to, you know, get this bucket to go, you know, anywhere it wants to on this. But if this is a frictionless pulley, then this pulley is going to want to be right in the middle. And why is that? It's because if we do have a pulley and you have a rope on both sides, what we just said is that the tension in this rope right here is the same tension on this side of the pulley. So if we say the tension in this side has to equal the tension in this side, then they have to be balanced. And if we have this bucket of weight, from a statics point, this would have to be right in the middle and equal distance. And it's still interesting because, like, even in this, when you have a pulley, it's like, well, both those tensions are kind of supporting this pulley, and this pulley is supporting this weight. And then so you can kind of just say, hey, maybe all the weight's just right in the middle of this rope, and then we have equal tension on both sides. But if we have equal tension on both sides, this is the, like, from the Newtonian perspective, if I do have a mass and I put a tension and I put a force this way, let's just call it T, this thing is going to be moving that way. It'll move that way, and then let's say we balance it with a tension force this way, and if we hold it, has no velocity to begin with, and then put those tensions on, it's not going to move because we don't have any resultant tension. And so that's why if you do have a pulley, the weight will be right in the middle. Now, if you have two dissimilar towers where one tower is bigger, one tower is shorter, I don't know. Is the weight still in the middle? I don't think so, because your angles change. Anyway, so that would be for a further problem. But the other aspect of this is that I think this gets confusing, because if you set up a slack line and you have like a really taut rope and then you stand in the middle, we know that the rope has like hella tension. It might be 10x your body weight. So if you're W, like the tension in the rope is like 10W, 10 times your weight. But then when we get a picture like this, for whatever reason, like mentally, I see a shallow angle here, and I kind of assume that there's going to be hella tension in this rope. But that's not true. The only reason it's true for, like, you know, something in the middle is because you just have very shallow angles. So high tension right here, and the component in the vertical direction, so we'll call it just Ty, and then you would have a component in the horizontal direction, Tx. Ty is the only thing that can support your weight. So our equation for this would be the weight down has to equal 2 times the tension in the y, since we have 2 of those. But the only way, or we could say the tension in the y is 1/2 the weight, you know what I mean? But the only way to get this to have any sort of substantial force is to really crank up, you really have to crank up this tension. You know, that's why it has to be 10x, just to get the horizontal component to have the right amount to support that person's weight. Alright, booyah. So in this example, hey, this is like a motor that's actually clenching the rope. And so what we have is like this scenario where, let's say I'm a person here and I'm holding, you know, I have to hold like this big old chunk of weight, and but someone else is at a shallow angle and they're like, oh, I'll help, and they're holding it up over here. So just take the problem to the extreme. You know what I mean? The next extreme would be like, well, let's say you're just totally holding the weight straight up, and then someone's like, oh, well, I'll help over here. And, you know, and then they're just like, am I being helpful by pulling this way? It's just like, well, not really. And it looks like this. So you take the problem to the extreme. It's like, no, this person is basically taking 100% of the load. This person ain't doing anything. So that's the visually what I can see from this problem, is you're going to have way more tension in this rope. This rope's hardly going to be doing anything. And even if you get to an angle of about a 45-degree angle, you're still taking, in the vertical direction, 70% of that load. So then this direction would only have to take, you know, 30% if that's what we have going on. Whoa, this last part I did not say right at all. So yeah, let's do this. Let's say we have a 45-degree angle, and this person has to basically kind of hold what seems like all the weight, and this person is just pulling this direction. He's like, yeah, I'll pull this direction, but now, like, what if this is the weight? How much will you have to pull? Well, I just said this angle, this component's only 70%, sure, but this is the only component that's actually helping. So this 0.7 of the actual tension that you're pulling is going to equal W. So, you know, this tension has to be more, because I can only take this bigger number, multiply it by 70% to actually get the weight. So, and then you would see that mathematically, that this weight divided by 0.7, you're taking this weight, dividing it by a smaller number, you know what I mean? So we have a number divided by a smaller number. Well, hell yeah, you get a bigger number. So this weight divided by 0.7, hell yeah, you're going to have to put more tension into that rope. And this 70% is 0.707. That's the square root of 2 divided by 2. Because that's 1.414 divided by 2. You can easily see, oh, that's like 0.707. Oh yeah, I've actually never done that. You know what I mean? It's good to know your these when it comes to fractions. So booyah, booyah. All right, so and that's what you would have. You would have that right here. So you would have weight square root of 2, 2 square roots of 2. So that would be your ratio. You would have 2 divided by 1.414. And yeah, what is 2 divided by 1.414? 2 divided by the square root of 2. Oh yeah, it's oh weird. 2 divided by the square root of 2. What you do is you rationalize this by multiplying by the square root of 2, and so this becomes 2 square roots of 2. We can factor out a 2, and you just get the square root of 2. Oh, that's bizarre. How we started with 2 square roots of 2, and then that's just the square root of 2. And I guess that makes sense, because 2 you could just write as the square root of 2 square root of 2. I think that's mentally harder to do, but you can see that that's just the square root of 2. Alright, hell yeah, so we're doing some mental math before doing this problem. So, but I kind of want to do this problem all in one go, so that was kind of the preliminary. So maybe I'll kind of start the video over again, and we're just going to straight tackle this problem. But I guess let's talk about our free body. Well, no, let's just do it. Alright, hell yeah. So we have a harder geometry problem from statics. I kind of put the intro at the very end of the video because we just want to go for this. One, we know that we have a pulley here, and so if we're pulling with a weight W, this tension in this cord is also going to be W. Now, the tension down is W, and we have 2 ropes that are equalizing. So I'm just going to, well, let's do this. We're going to call this tension AB and this tension BC. And so in our Y direction, to actually support this weight is going to be down. We have to equal it with the upward components. And so that's what we're going to do. So we're going to say, hey, we're going to take the tension AB, and we're just going to take the vertical component of it, and then that has to, and add it to the tension BC, but just the vertical component of it. Cool. So when we do those, that's our equation right there. Now in the x direction, because we actually have some tension in this and some tension in this, and they're not, the angles are not balanced. And so we have another equation that says, and this tension pulls in the y direction. So, I mean, we basically just have this tension opposing this tension, and those 2 components have to be the same. And not the tensions. These tensions can be different, but the component this way, because this is a shallower angle, so actually it's pulling more this way. And so that means that this has to be a bigger number. Cool, because it's pulling less this way. And in the intro, I show you kind of the opposite way of that, because, hey, most of the weight is under that, so hell yeah, this is going to be the bigger number. But in this x direction, yeah, this component's going to be a larger percent of this. This component in this direction is going to be a smaller percent of this. So that equation is going to be TAB in the x direction that way has to equal TBC in the x direction that way. Maybe I'll just throw a little, vectors on those. All right, so those are our equations. But what we want to get to is why this is kind of a harder geometric problem. So I'm just going to draw this triangle. And so I guess let's read it. 2 identical weights are supported by a cable that runs over a frictionless pulley. Now this joint is a joint. There is no pulley here, so it's a fixed point on the rope. It says compute the distance x for where this system will remain at rest. You know what I mean? So, hell yeah. And why I think this is a complex geometry problem and a cool one is because you don't have to find any angles. You know what I mean? We don't have to find that angle or this angle. We can just use Pythagorean's theorem like outright. And so yeah, that's going to be pretty sweet. So here's our hypotenuse. That's going to be 8. This total distance is 10, but what we're trying to shoot for is figuring out any sides of these triangles. We want to know the side of the triangle, 100%. And so we have this term x right here. So sweet. So this is just going to be x. And then we have to use, like, this comes up all the time in trigonometry. It's just like, well, if this is x and I know this is 10, then this is going to be 10 minus x. It's just going to be that. So we have 10 minus x right here. Pythagorean's theorem says that a squared plus b squared is equal to c squared. So this squared plus this squared is equal to the hypotenuse squared. We don't have this. So that also says, and you should be able to do this kind of in one go, the hypotenuse squared minus one of the sides squared is equal to the other side squared. And that's pretty easy to remember, because to get this, you're going to have to square this and add it to the square of this to get the larger number, the square of this. But if you're just trying to find the side and you're already starting with the larger number, you have to square this and then subtract the other side. So that's kind of how I remember it. So we're going to, so let's do that. Let's find this, and it's going to be 8 squared minus x squared. And then we're going to, so that's this squared, but this is actually the square root of that. So if we want to find side b, we're going to say b is equal to c squared minus a squared, and then taking the square root of it. So this is kind of the fundamental equation that we're going to use for this video. All right, and then here's what I do for trigonometry. Is I always say, if I know 2 things about a triangle, I know everything about it. And so in this case, especially when we're doing variables, sure, it's just like, yeah, that still counts, even though we need to solve for these variables later. But when it comes to a right triangle, you already know, like, hey, one of the angles is 90, but you literally just need to know 2 things. Either 2 of the sides, you know everything about the triangle, or one of the angles and one of the sides. But since we're just sticking with, we're not using any angles on this, and the cool part will come in a second. Yeah, all we need to know is that if we know 2 sides, we know everything about the triangle. That's what we just did right here. We knew this side, we knew that side, so we know this third side. And then, since we know this third side, and it's common to this, I mean, hey, this triangle over here, we know 2 things about it. So now we know everything about this triangle, and now let's use that process to find this hypotenuse. It's going to be this squared plus this squared, square root that. So we're going to have this is going to be, this squared is just going to be 8 squared minus x squared. That's all I did there. Plus 10 minus x, this squared, and then the square root of it. So again, we had 2 sides, like a and b, and we want to know c. So we had this squared plus this squared, square root that. That's going to be c. And maybe I should have wrote that one. So if I have a squared plus b squared is equal to c squared, c is equal to a squared plus b squared, and then the square root of that. So that's the other equation that we're really using for this video. All right, so now what do we do with this? Well, in statics, we want to know, like, the component in a direction. And so if we knew the angle, like let's say we're pulling with like 100 pounds at a 30-degree angle. We want to know this component and this component. And so how we do that is we'd be like, well, this is the sine component, and I know I take 100 sine 30. And that's going to be 100 times 0.5. Cool. And then this is going to be the cosine component. It's going to be 100 cosine 30. It's going to be 100 times 0.866. Cool. So how do we do that using like the Pythagorean theorem and just geometry? Well, this says is the Pythagorean theorem, or kind of the other way, I guess the other way to do this is to say, all right, let's take a step back. So we're going to have this tension in this chord is going to be tension AB. We just want to know the percent. That's all we're interested in, because sines and cosines right here, this is the percent in the vertical direction. This is the percent in the horizontal direction. So if I have geometry, all I want to know is the percent of this in the vertical direction and the percent in the horizontal direction. And so how we do that with geometry is we say, well, whatever this distance is right here, divided by the hypotenuse is going to be that percent. So the percent of TAB in the vertical direction is just the percentage is going to be this divided by the hypotenuse. It's going to be the length in the vertical direction divided by the bigger number, the hypotenuse. So that's going to be 8 squared minus x squared divided by 8. Cool. Now the percent of TAB in the horizontal direction is going to be the this distance, x divided by the hypotenuse. Cool. And it's hard to tell what these percentages are, but I mean, you could go back and double check just by from the picture. I always take your hypotenuse, kind of divide it by 2, and then see how that compares. This side is definitely more than 50%, so maybe this side's 0.6, and then maybe this side's 0.8, and maybe it's a 3, 4, 5 triangle right there. You know what I mean? So this is 60%, this is 80%. So I could go back after doing this problem and double check that my vertical component, this probably has to be about 0.6, this probably has to be 0.8. So that would be a good double check on reality. Whoa, and that's tripping me out because I did not do that in this problem. So we're going to do that at the very end because some of these problems, like, is this even drawn to scale? You know what I mean? If this is the setup, is this actually even drawn to scale? And knowing what I know about the answer is like probably not. You know what I mean? Okay, but let's move on. So we have two separate tensions here. Again, because this is a fixed point, this is not a pulley. We do not have equal tension in both these ropes. If we did, it would just be right in the middle. We could just, you know, like figure that out right away. Is that the tension would be all the same, and then it would have to be equal. And again, the reason why the tensions can be different is, yeah, this is fascinating. I have to kind of catch myself, is because we're fixing to the rope. We're not allowing this point to get to the center. So if this rope was hella long and could actually, you know, like, let's say this rope was just really, really long to the extreme and it was this long. Well, it would be way down here. Oh, well, actually, I don't know how this problem changes. Yep, that would be actually, I'm going to pause on that. Like, that would be a good one to do, is just like, well, like, let's say this rope is 10 meters. How does that change the problem? And let's say this rope is, I guess, really short. How does that change the problem? And let's say this rope could be hella long too. But anyway, so let's get back to kind of the meat of doing the problem. Is we're finding the percentages. So this tension right here, we know it's W. That's the one that we do know. But we want to know the percent in the vertical direction. So we're going to go TBC, and we want to know the percent in the vertical direction is going to be, by geometry, it's going to be this distance divided by the hypotenuse. And that's the only bummer about doing with this method, is that you have square roots. It seems like things are more confusing than they need to be. And even right here, I'm going to square this. So we're going to have 100. Actually, for my problem, I just do it 10 squared. So we're going to have this squared, and then we're going to have this squared as x squared, and then we're going to have the middle term. That's going to be negative 10x, and we're going to have two of those. So we're going to have negative 20x. Yeah, let's do this just to make sure we get it. So we have 8 squared minus x squared plus 10 squared minus 20x, and then we have plus x squared. So even this term we can factor out. We have a negative x squared and a positive x squared. So this term becomes 8 squared plus 10 squared minus 20x. Alright, sweet. So we're going to have 8 squared plus 10 squared minus 20x. Sweet. So this hypotenuse is going to be right there. Cool. Now we have the percentage of this tension in the horizontal direction. And that's going to be, and I'm glad I'm not doing this all in one go, because this is the meat of the problem. Is like, well, we just need to find the percentage in that direction. And the percentage is this function of x, but nothing else. Like it's literally, if we knew x, we would know the percentages. Okay, so the percentage of this tension in the horizontal direction is this horizontal distance, 10 minus x divided by the hypotenuse, which is right here. So we have 10 minus x divided by the square root of 8 squared plus 10 squared minus 20x. Now I could have just said this is 164, but I'm just going to keep it like this. Alright, so I'm going to rewrite this. I'm going to redraw the triangle, and and then we're going to rewrite these, and then we'll go through the equations so we can finish just on one sheet. Alright, hell yeah. So all I did was just redraw this geometry because it's just good practice to go over those components. And so now, even though we kind of wrote this y and x, if we're going to the extremes of like, hey, just kind of using this method to figure out the percentages of this tension in the vertical and the horizontal, we should also probably be able to pull these equations just kind of, I guess we're going to do the equations in the y, but we're going to do it just all the way through. So in this y direction, we have a weight down. It has to be balanced by the vertical components of both these tensions. So we have the tension here and the tension there. Cool. So we're going to say W has to balance with this tension. For now, I can just call it TB. So we have this tension, but we need to know the percentage of that tension, and that percentage is going to be this distance divided by 8. So we have the square root of 8 squared minus x squared divided by 8 times the tension AB. Cool. And then we're gonna, so the weight down has to be balanced by that vertical component of the tension plus the vertical component right here. So we're gonna have the tension BC times that percentage. That percentage in the vertical direction is this distance divided by the hypotenuse. So here's how we got this this hypotenuse. We took this squared plus this squared, square root it, and this is how we simplified it. This was 10 squared, so those add. Then we had, the middle term is negative 10x times 2. That's going to be negative 20x. And then we get a plus, negative x squared becomes a positive x squared. That cancels out that. So that's where we have here. Okay, so the vertical component is going to be this divided by that. So we're going to have 8 squared minus x squared divided by 8 squared plus 10 squared minus 20x. Cool. And that's going to be the tension BC. Okay, so there's our equation. Now, we could just, from what we know is that, hey, if this is the tension in this rope is just W, and it goes around a pulley, so the tension BC is equal to W. And I'm not doing anything more fancy about that. I've done videos where you can actually, chop up the rope, do free body diagrams of the rope, and then follow it around a pulley, and then just know that the tension around a pulley, this is just kind of what we know about pulleys. There's no friction there, and so the tension on one side is equal to the tension on the other. So sweet. So we have that as one of our equations. So right here I could just put W. Alright, now in the x direction, we're going to have the horizontal component of this tension, the percentage of TAB in that direction is going to be, by geometry, is going to be x divided by 8. So we have x divided by 8, TAB, and that has to equal, the tension this way has to equal the tension that way. This weight has no component in this horizontal direction. So these two tensions are the only thing that have to balance. If they didn't balance, well, then this weight would move that way. This weight would, like if this tension was stronger in that direction, this weight would move that way until Yeah, it's just fascinating. Until it balances, or if it doesn't balance, it doesn't balance. Alright, but now I can mentally walk through this, yes, because the tension in this one, because of this pulley, can only be W. You know what I mean? So if this tension is higher than this thing is going to move that way. And then while it does, what happens is that this becomes shallow, and alright, hell yeah. This problem is tripping me out, because this rope could be as long as it needs to be. And if AB was directly under here, you would have a weight, but then you would have something pulling it this way. And so, you know what I mean, that would pull it in this direction. And because this component would only have a small horizontal component, it can't balance like that huge component that's pulling it this way with that W. So until they balance out, yeah, and it's just kind of interesting how this angle gets steeper, but then at a certain point, when this gets really high, if this was way up here, it would only go over to 8, and then this angle, you know, because if this rope was down here at 8, and this was as long as it wanted to be, yeah, that's just kind of interesting. This angle is less. This angle gets steep through here, but then at a like steep this way, and then at a certain point, this angle goes back. But hell yeah. But we're not gonna overanalyze it. We're just going to you know, kind of use what we know is that the tension this way has to equal the tension that way if it's supposed to be balanced. And so we have the percentage of the tension AB was, again, this x divided by the hypotenuse. That has to equal the percentage of the tension BC in the horizontal direction. So that's the horizontal direction percent is this distance divided by the hypotenuse. So we have 10 minus x divided by 8 squared plus 10 squared minus 20x. And then multiplied by the tension BC. So this is the percentage in the horizontal direction. And if you go back, you know, I mean, those are going to match. This is tension AB in the horizontal direction, tension AB in the horizontal. Tension BC in the horizontal direction was what we had for that. This was in the vertical direction. Tension AB in the vertical direction was that. So that's what we have. Tension BC in the vertical direction was this divided by that. Yep. So, and I just don't think this is trivial. I think using sines and cosines and just knowing that you know, as long as all my angles are starting from the horizontal, and, you know, sine of an angle is always a vertical percentage, and sine is definitionally a percentage of the hypotenuse in that vertical direction. Usually your hypotenuses are your vectors. You know, I mean, they're your force. The tension in AB is the hypotenuse. It's the larger number. So the components in the vertical and horizontal have to be smaller, or percentages of that. And just when you see cosine of an angle, it's just really easy to be like, okay, there's my percentage, there's my percentage. But when working with Pythagorean's theorem and this idea that taking this distance and dividing it by the hypotenuse, what this gives you is it's the definition of a what is it called? Like a unit? Is it called a unit vector? Yeah, so at the end of this video, maybe I'll go over, or for a separate video, I'd be like, whoa. So the cooler way to do this would be take this geometry, knowing that this geometry is just allowing you to get the percentages. But that's the wild thing. This geometry has nothing to do, like this number 8 is just relative to this number x. And that's it. Like, this is just a triangle. If I took this triangle right there, I could do the same thing. Whatever, let's say this value was 2, and this value was x divided by, 4. 1/4 x, this was 1/4 8. Like, yeah, now we just have similar triangles. Yep. So it's just fascinating how you would do that. You would take your hypotenuse and make your hypotenuse 1. So if we have 8 right here, we would just do 8 divided by 8, and we would do x divided by 8, and we would do this hypotenuse divided by 8. Now this is 1, and then this is a percentage. It's a proportion of the hypotenuse. So I think, yeah, that's the more legit way from the fundamental perspective to do it. But, it's just like maybe one more thing to do and your terms get a little messier, where it's just kind of nice to know that this divided by the hypotenuse is the percentage in the vertical direction. Like that from statics is something that, man, I mean, it's a fundamental way to solve statics problems, and for whatever reason I was able to graduate without doing it that way. I was just sines, cosines till graduation. But yeah, such a cool way to go back and do it this different way. And how it relates to unit vectors. How, yeah, this number 8 isn't really that meaningful. You could do 8 divided by 8, and then all these divided by 8, and now you have a hypotenuse that's equal to 1. And these are the percentages in that direction. And what we know about the unit triangle, where we have 30 here, and this is sine 30, and this is cosine 30. Well, hell yeah, if this is 1, hell yeah, this distance is 1 times sine 30. This is 1 times cosine 30. That's 0.5, that's 0.866. And when we use Pythagorean's theorem, 0.5 squared plus 0.866 squared, square root that is equal to 1. And let's do this. This is 1/2 squared. We said that cosine, maybe we didn't, but cosine 30 is the square root. Like, and this is a good one to do, just be like, what is, I like to use the decimal forms, but just know that these are all related to like squares and cubes, like the square roots and cubes roots. So if you get something like, even if it's like the 45, sine and cosine is 0.707, I need to do this as a fundamental. Just double it. I mean, cool. That's going to be 1.714. I'm sorry. That's going to be 1.414. Oh yeah, and then you can be like, oh yeah, no duh, that's square root of 2. But I think it's really difficult to see that this is square root divided by 2. It's equally difficult to see this is square root 3 divided by 2. But if you take 0.866 and multiply by 2, always a good skill. And I can't even do that. 16, 17? Hell yeah, 0.1732, and now I know, if I know this, I know that. So that's kind of fascinating. So this is square root of 3 divided by 2, so let's go back here. We're going to have square root of 3 divided by 2. We're going to square it, take the square root of it. So we have a lot of things going on, but like back to the fundamentals. If I'm squaring this fraction, I can square the top, square the bottom. Cool, moving on. I can square this, I can square the top, and then square the bottom. And then we're going to take the square root of it. So this becomes 1/4. This becomes plus 3 divided by 4. Oh, whoa, okay. So we have 1/4 plus 3/4. That's the square root of 1. That's 1. All right, hell yeah. So the reason I did that, I'm trying to think of why I just did that. Oh yeah, it was to show you that, yeah, these sine components and these cosine components are percentages. And those percentages, when we square them, when we square this percentage, or this percentage or fraction of the hypotenuse, percentage of the hypotenuse in a fractional form. Because if I have 0.5 and I multiply by 100%, that's 50%. But 0.5 is its fractional, 0.5, we all get that. But yeah, this component, so if my hypotenuse is 1, these are the components. Either like thought of as a percentage or a proportion, 0.5 of 1. That's 50% of 1. This is 0.866 of 1. And so when I take those proportions and square them, and then add them and take the square root of them, I get the hypotenuse. And when the hypotenuse is 1, well, sweet. Taking this squared plus this squared has to equal 1 as well. So hell yeah. So I was just reiterating why when we do like this divided by that, we're still getting a percentage. And let's talk about this one more time, especially with this unit of like 1, 0.5, and 0.866. If I divide this by 8, this now becomes a unit of 1. And then I would have to divide both these sides by 8. And then when I do that, the proportion over here is going to be square root of 8 squared minus x squared divided by 8. And the hypotenuse is 1. So then, by definition, what have we been saying? The vertical component is going to be this divided by the hypotenuse. Well, if this is already the square root of 8 squared minus x squared divided by 8, and then if I divide that by 1, it's just what we have right here. So, we don't have to turn this triangle into a unit triangle. We can just say this divided by the hypotenuse is that same ratio that we just talked about. So yeah, so that was the reason of comparing it to a unit triangle, comparing it to sines and cosines, so we're not freaking out that it's a totally different thing. All right, so let's get back to it. So now we have our in the x direction. The percentage of this in the x has to equal the percentage of this tension in that direction, and we know that C is equal to W. So I'm just going to throw that in right here. I'm just going to throw a big old W, because now we want to know, like, what do we know and what do we not know? We have one variable there. We don't know the tension in AB. For this problem, we're just given W, and we're just going to assume that we know what W is. So the only other variable is we don't know X. So we have one equation, two equations. We don't know the tension in AB, and we don't know X. So what we need to do is solve for this tension in AB, and then shove that into here. So you can kind of see where this gets messy. But let's try to write a little bit neater. So we have tension AB. Now I'm just going to bring the 8 upstairs and then the X downstairs. So I'm going to say this is 8 times 10 minus x. And this is, take the x downstairs. X square root 8 squared plus 10 squared minus 20x. Cool. And I could FOIL all these through. I did that in like the first time I did this video, but I just kind of made more errors, so it's just kind of fascinating. And I'm even forgetting my W. Alright, got some more juice in the camera. So we have the tension AB is going to be, we just solved for, basically that. And we're going to put that right into there. And we're going to use this equation. I'm going to, sorry about this, I'm going to get this W, I'm just going to flip the equation. The W is going to be over here. We're going to work on this first and then equal to W on the other side. So this equation says the square root of 8 squared minus x squared divided by 8 times this TAB, so that's all this. So we're going to have 8, 10 minus x, x square root of 8 squared plus 10 squared minus 20x. We still have this W. Alright, now we're going to add this part. 8 squared minus x squared, square root of 8 squared plus 10 squared minus 20x, W, and then this is going to equal W. Okay, so here is where, there's a few places where you have to know a few things about math, and, here's one of them. You're like, well, we have a W in all these terms, so it's irrelevant. We can factor out a W everywhere, and it doesn't matter what the weight is. This angle will always be the same. So if this problem was 2W, like twice the weight here, twice the weight here, it's still going to be in the same position. So that's what this part of the equation, when you can get rid of that. Now this just drops, I mean, how you would drop this out is by dividing by W everywhere, and this just becomes 1, this just becomes 1, and then this just becomes 1. Cool. So we definitely still have a 1 here, and then we just get rid of those terms. All right, booyah. So now what we have to do is we have to add these two terms. And again, another thing from math is if I have two fractions and I want to add them, well, make sure your denominators are the same. And so this one has an 8x and then a square root of this. This one doesn't have an 8x, but it still has the square root of this. So this is the only term over here that this side needs. So let's multiply top and bottom by 8x. Okay, hell yeah. Since we did that, now we can add these straight up. And so on the top, these are all products. We have this product, that product, 8x multiplied by this. And we're going to add these two things. Now, things that I can see are similar in both of them are for sure this. So I'm going to factor that out. So I'm going to have 8 squared minus x squared. And I don't know if you'd be able to see this right off the bat, but I can factor out the 8 as well. So let's do that. So we're going to have 8, the square root of 8 squared minus x squared. And then so now and we factored out the 8. So now over here we're going to have 10 minus x, and we're going to add it to, we just have x. So because we factored out this and an 8, we factored out the 8 and this. So we still have that x there. So we're going to have 10 minus x plus x. And then these two x's drop out. Cool. Now we're going to, now the denominator is just one term. It's just going to be 8x square root of 8 squared plus 10 squared minus 20x. And we can factor out this 8. Cool. And now this is equal to 1. And now we can take this and multiply it up there. So now we can get this is equal to that. So, yep. I'm just going to save paper, and I'm just going to say, hey, this, well, no, we'll do it. So what do we have over here? We have 8 squared minus x squared, and then we have times 10. All right, I'm just going to put the 10 out in front. This is going to equal, we're going to take this upstairs, x, 8 squared plus 10 squared minus 20x. Okay, so now this problem is cool. I mean, I think the bread and butter was figuring out the percentages. I mean, this dimension divided by the hypotenuse is the percentage of this tension in that direction. And then, obviously, the horizontal components. But the other part of this, there's just a bunch of different math things that come up. Like, hey, factoring out, dividing by w's to make all those 1. It's not even a function of the weight. What was the other one? Oh yeah, adding two different fractions that aren't the same, getting the denominators to be the same so you can add those. Cool. And so here's probably the third and last one, is that if we want to get rid of this square root, we have to get this inside the square root. So how we do that is we have a product, and we need, the way to get things inside the square root is make both terms have a square root. So I don't know if I did this at the beginning of the video or just about 2 seconds ago. No, it was when we did the square root of 2. Like if I have 2 and I want to make this into a square root. Hey, what is 2 of? Well, it's a product of, like I need a product of two things. So I could do square root of 2, square root of 2. And now I could say this is going to be the square root of 2 times 2. Get it inside. And then I could say that's the square root of 2 squared. So this is maybe the more difficult way to see, like, oh, I never knew 2 is just the square root of 2 times square root of 2. But here is just like, well, I already have a square root term here. I need to turn this into a square root term. But that's the same thing we just did right here. 10, well, what's that? Well, that's the square root of 10, square root of 10. Cool. So then if I can get it inside, it's going to be the square root of 10 times 10, and it's going to be the square root of 10 squared. Yeah, that seemed actually complex to me to go through that. I can just see that, hey, if I have 10 here, I need whatever I multiply still has to equal 10, so I'm just going to say that's the square root of 100. So obviously that's the faster way to do it. And then I'm going to have square root of 100 times 8 squared minus x squared. And now because I have both things with a square root, I can put this inside. It's still a product inside, so we're going to have the square root of 10 squared. That's going to be that 100. I'm going to keep it as 10 squared. And then multiplied by 8 squared minus x squared. So that's how you get that 10 inside that square root. Same thing over here. To get this 10 inside, I have to do x squared square root that. Hey, these are now similar. X squared square root is the same thing as x. And since I would have this times this, with the square roots as the product, I have the square root, and we got the products of 2 square roots. I can just do this where this term is just multiplied by the other term. You got to make sure to multiply them once they get in here. But now let's do all this in one go. We're going to have inside, we're going to have that x squared. We're still going to have the square root, but we're going to have x squared times 8 squared plus 10 squared minus 20x. Okay, hell yeah. And then I'm going to just FOIL this through. So we're going to have 8 squared plus 10 squared. That's going to be x squared minus 20x cubed. Okay, damn it, I'm kind of running out of space. And so let's just rewrite this. So we have bummer, kind of lost the square root. So yeah, so we have this side still has a square root on it. So we have 10 squared, 8 squared minus x squared square root is equal to the square root 8 squared plus 10 squared x squared minus 20x cubed. And I guess I didn't need to do any factoring right there. I didn't need to do any other factoring. Right here, I could have just said, hell yeah, we got both things underneath the square root. Now we can square both sides. And that's kind of fascinating. We have an equation that says like 2 is equal to 4. So, no, holy hell. No, we have an equation that says 2 is equal to 2. If we square both sides, we'll have an equation that says 4 is equal to 4. I swear, sometimes it's just like, well, you can square both sides. You can divide. You can take the square root of both sides of an equation. You can take an equation and divide everything. You can divide both sides by a number, w. You can multiply both sides by w. So as long as you have an equation, you can do those things. And where I get confused is like, if you have a fraction, 1/2 plus 1/3 is equal to 1/4, you can't say this squared plus this squared is equal to that squared. That is what you can't do. You could say this whole thing squared is equal to that square, but maybe that doesn't get you that far. Alright, so we can square both sides. And so we're going to have 10 squared, 8 squared minus x squared is equal to 8 squared plus 10 squared x squared minus 20x cubed. And did I even do this right? Yeah, we did. Yep. But yeah, I should have done all my factoring after I got rid of the square root, because we got to factor this side as well. So we're going to have, this is going to be 8 squared times 10 squared minus 10 squared x squared is equal to 8 squared x squared plus 10 squared x squared minus 20x cubed. See, I maybe just get just a little bit messy, but we have x squareds and we have an x cubed. I want to get it all to one side, so we're going to say 0 is equal to... Yeah, and I even feel like I made an error, but maybe not. Yeah, I thought this term should be positive, but when I bring it over there. All right, no, we're good. So I just kind of double checked, but hell yeah. So we need to get everything to one side, and so let's get the let's get this x cubed first. So we have negative 20 x cubed. And then we have all these x squared terms. So we're going to have plus, I'm just going to add them all up. We have 8 squared plus 10 squared. And then over here we're going to have another plus 10 squared. So that's going to be my x squared terms. Cool. So 1, 2, 3. The only other term we have is a constant. So we're going to have minus 8 squared times 10 squared. Cool. And I'm glad I did it this way because, you know, if you did an equation, you could go back and put in your variables. You know, 8 is going to be this hypotenuse, 10 is going to be that distance, and you know, it's just a little bit easier to go back and put variables in. Okay, but now we have an equation that is this is your equation that you have to solve for x. And yeah, we don't have any term that's just x on its own. That's kind of fascinating. All right, so, and then I'm just going to put that in my calculator. So we have negative 20 x cubed plus, all right, so plus parentheses 8 squared plus 10 squared plus 10 squared x squared minus 8 squared times 10 squared. Cool. And then what we're shooting for is x to be somewhere between 0 and 10. And so, heck yeah. I don't know, we can make a, let's do 100. Let's just see what this kind of graph looks like. Yeah, it's a really steep graph. Value 7.4. We're gonna find we're gonna do a left bound and right bound on that answer. I actually don't know how to solve for x cubes. You know, I mean, maybe I will look into that. But we do have a solution. X is going to be 7.4787754. X is 7.48 meters. So there's 3 digits, and booyah. So I don't know, that was kind of cool. The other, like, I guess I've been told not to use your calculator as a crutch, but what I would use your calculator for is to, especially, there's so many places I could have made errors in here, and I did go, my first go around, I made tons of errors, and it was kind of frustrating to go back and find them all. And so I'm going to take the rest of this video to see how fast you can get, because once you get to this answer right here, you don't have to use all those mathematical tricks. You already have one equation that is a function of x. Take everything to one side and graph it and just get your answer. So we're gonna finish with that. And this will be good to see how fast I can do a problem. You know what I mean? I don't know if I'm going to make a separate video, but let's do this. Let's race through it. Alright, hell yeah. I just want an accurate answer and a fast answer, so let's go for it. This weight is being pulled down. It must have to be supported in the vertical direction. And so we're going to draw our triangle. This distance is x. This is 10 minus x. This distance is 8. So this hypotenuse is going to be 8 squared minus x squared square root that. Now this hypotenuse is going to be 10 minus x squared plus 8 squared minus x squared, square root that. We're going to have 10 squared plus x squared minus 20x. That's going to cancel. And this hypotenuse is going to be 8 squared plus 10 squared, getting a little bit messy, but minus 20x. Hell yeah. So now I have that. Now I'm going to get my vertical components. I'm going to say this weight down is equal to this tension. I'm just going to call this T. I know this tension is W. Get on with life. So we can say the percentage in the vertical direction. That's going to be 8 squared minus x squared divided by 8 times T plus the tension of this one in the vertical direction. That's going to be 8 squared minus x squared divided by this hypotenuse. 8 squared plus 10 squared minus 20x. And that's a W. Sweet. And then in the horizontal direction, I know that x divided by 8 times T has to equal 10 minus x divided by this. 8 squared plus 10 squared minus 20x is equal to W. Cool. So then I can say that solve for this tension. This tension, and if we're doing this real fast, I can just say this tension is 8x. Booyah, did it. And then I shove this tension right into there. And cool. So yeah, I guess we'll do that. So we're going to have the square root of 8 squared minus x squared divided by 8 times 8 times 10 minus x divided by x square root 8 squared plus 10 squared minus 20x. Cool. And then this is going to be multiplied by w. We're going to have plus, now this term, 8 squared minus x squared, 8 squared plus 10 squared minus 20x. Hell yeah, that's times w. So this equation is equal to w. W's drop out. This is equal to 1, or I could just say this is minus 1 equal to 0. So this is the first place that I can actually type this into my calculator. I have one equation, and it's for x. Now, instead of going through the mathematical I can't say karate terms. But anyway, we can just throw this into our calculator and get the answer. So let's start with this term. We have square root 8 squared minus x squared. All right, n square root divided by 8. I'm just going to factor out an 8. Hell yeah. All right, so now multiply by 10 minus x. Now we're going to divide by x, and then divide by the square root of 8 squared plus 10 squared minus 20x. All right, hell yeah, did it. That's that term. Add it to this, the square root of 8 squared minus x squared. All right, divide it by the square root of 8 squared plus 10 squared minus 20x. All right, booyah. And then minus 1, and we're just good to go. I'm going to go zoom 6, that action, and we're going to get an equation. Now, it's going to be different than the equation that we saw before, but it's going to have the same answer. So I'm going to go value 7.4, 0, left bound, right bound, and then, heck yeah, we get x is 7.4787754. So x is 7.48 meters, and that's our answer. But it just shows you just a way to be like, hey, you're going to get some equations, equation 1, equation 2, and then the equation, that was it. Well, and then I guess the weights dropped out. We substituted t in for there, and it was just solving for x. And so, yeah, that was the first opportunity where we get our equation with one variable. And, it's just good to have this in your playbook, just because, like, I'm going to make 100 mistakes, and there's no way I can do the math, get to the end, and get a correct answer. So this was a place to be like, heck yeah, I can just throw this into my calculator, and double check after I do the math. So booyah. Alright, hell yeah. So we have a 1-star statics problem, and this is Pythagoras. And what we're going to go over is kind of using Pythagorean's theorem. We're going to divvy up this triangle. And then we're also going to turn the triangle into a unit triangle. And that's going to help us determine the percentage of these. So we have a tension here and a tension here. And so those are vectors that are holding force, and they have a direction. And we want to know their vertical components and horizontal components. So we're going to have kind of two vertical components. This one is going to have a vertical and a horizontal. This tension has a vertical and horizontal. So that's kind of the first thing that we're going to do is draw these two triangles. This distance x is where the system is in equilibrium. We don't know where that position is going to be. This whole distance between is 10. So if this is x, this distance has to be 10 minus x. So that's kind of how I do that, 10 minus x. This hypotenuse is 8. So my axiom is especially with right triangles, if you know two things, you know everything about this triangle. So I know both these two sides, so I know this side. Now, if I knew these two sides, it would be this side plus this side squared plus this side squared. Square root that is equal to this side. So we have a squared plus b squared is equal to c squared. And then you could solve for c. You could say c is the square root of a squared plus b squared. But if I want to solve for a side, I would say b is equal to c squared minus a squared square root that. And just an easy way to understand this is if I want to know this side, I'm going to square the hypotenuse. I'm squaring the bigger number, so I must have to subtract the square of the other side. So this term right here is going to be the hypotenuse squared minus the side squared, minus x squared, and take the square root of it. So that's going to be this equation. Cool. Now I come over to this triangle. I know two different things about it. Since I know two things, I know everything about it. So I know the hypotenuse, and this is going to be this equation. You know what I mean? This side squared plus this side squared, square root that is going to be this hypotenuse. So this is going to be this squared is just going to be 8 squared minus x squared plus this squared is going to be 10 minus x squared. Cool. And then we're going to take the square root of it. Now right here I'm definitely going to simplify this. I'm going to say 10 minus x squared. The way I do this is like, well, I'm gonna have that first term squared. I'm gonna have this second term squared. The negative for sure goes away, so plus x squared. And then I'm gonna have the middle term. This multiplied by this is negative 10x. I'm gonna have two of those, so negative 20x. All right, hell yeah. So this becomes 8 squared minus x squared plus 10 squared minus 20x plus x squared. And let's see if we can simplify anything. This negative x squared cancels that positive x squared. Sweet. So we finally have this hypotenuse. It's the square root 8 squared plus 10 squared minus 20x. All right, booyah. So now we, okay, and I said we're going to do this video by getting this into a unit, a triangle that's a value of 1. I don't know if I'm going to explain why we're going to do that, but we're just going to do it. So if this triangle has a hypotenuse of 8, this side is x, and this side is this equation right there. And I want this hypotenuse to be, a unit triangle is where the hypotenuse is 1. So how do I get this hypotenuse to be 1? I just divide by 8. And if I do that, I got to divide everything by 8. So I'm going to say x, I'm going to go x divided by 8, and then I'm going to have this divided by 8. Oh, I'm sorry, this was this hypotenuse. So I'm just focused on this triangle right here. So this hypotenuse was 8. To make it a unit triangle, I got to divide by 8. Divide everything by 8. Cool. But I guess before we do that is we need to probably separate the two triangles if we're going to do that. So I'm going to take this triangle and then have it separate from that triangle. This unit triangle is going to be 1. That's going to be 8 divided by 8. I see that. That means this has to be x divided by 8. And this has to be the square root of x squared minus x. Square root of 8 squared minus x squared divided by 8. So now this is a unit triangle. To get this to be a unit triangle, well, we have a hypotenuse that's this. So to get this hypotenuse equal to 1, we got to divide by this whole thing. All right, let's do that. Or I'm not going to write that, but now I'm going to have this hypotenuse is equal to 1 once I do that. If I divide this hypotenuse by itself, I have to divide this also by that. And I'm going to totally run out of space. So we have this part of the triangle, hypotenuse of 1. This side is going to be 8 squared minus x squared divided by the hypotenuse. And just so we're on the same page, this triangle is, used to be 10 minus x, this, and then the hypotenuse used to be this, but we're dividing it by itself. So let me write that in. And then we have to divide everything by that, by this number right here. So that's what we're dividing everything by. So that's what we just did for that term. Now this term becomes 10 minus x divided by 8 squared plus 10 squared minus 20x. Sweet. All right, so now why did we do that? Is because we know this tension is going to be in that direction. And so if there's our vector for tension, we can know the percentage in the vertical component and the horizontal component. Now it just definitionally spells itself out. So let's look at a unit triangle of hypotenuse of 1, and let's say we know the angle. So this side is going to be sine theta. Well, it's actually going to be, this length of this side is going to be 1 times sine theta. It's going to be the hypotenuse times sine theta. I like to think that sines and cosines are the percentage of the hypotenuse. So this side is going to be the cosine side. We're going to have 1 cosine theta. It's the percentage of the hypotenuse in this direction. So you can see that the 1's are redundant, and now we're just left with, as long as the triangle has a dimension of 1 for a hypotenuse, the sides of the triangle will be the kind of the percentage component. And the percentage as a fractional percentage. So if this is a 30-degree triangle, this side is 0.5 when the hypotenuse is 1. This side is 0.866. Another way to look at that is if I split the hypotenuse into 2, hey, this length is basically equal to that length. And you can visually see that. This length is 1. This length is slightly less than 1, so that's where it's 0.866. So it still is a fractional representation of the hypotenuse, but I definitely think it's cool to think of it as a percentage, because that's kind of what it is. It's 50% of this hypotenuse is in that direction, so 0.5. Cool. And And I'm just doing it this way because it shows you that if you get down to a unit triangle, this is your percentage. You know what I mean? This is that percentage in the vertical direction. This is that percentage in the horizontal direction. I don't know I don't know of a symbol that represents a fractional percent. You know, so that's why I just do percentage. Obviously, this isn't going to give you 80. This isn't going to, like, let's say this is 1. You know, just, hey, let's see what this is. Split this into 2. Well, this looks about like 60%. This number is not going to spit out 60. It's going to spit out 0.6. Now, if this is 1, this looks like about 0.8. This number is not going to be 80. It's going to be 0.8. So it's not a percentage, but it's a fractional percentage. But as long as your hypotenuse is 1, this is that fractional percentage in that vertical direction. Okay, sweet. So that's useful because from this geometry, now we can say that if we do have tension AB, and the tension in this chord is just going to be W, so we have tension W. So those are our tensions. And we're going to have 2 components. The vertical component of W is going to be, this is going to be the component. So this times W is that vertical component. This times W is going to be the horizontal component. This times that tension AB is going to be the vertical component of this tension. And this x divided by 8 times TAB, the tension, is going to be the horizontal component. Cool. So that's when we can then use our statics equations that if this force is pulling down with the weight W, the 2 vertical components have to equal W, just to make sure this thing is static. That's the whole point of the statics problems. It's like, hey, this thing's not going to move, so the forces have to be balanced in the vertical direction. This weight is not putting any horizontal force. So then we have to say the horizontal component of this tension has to equal the horizontal component of that tension. So then we would say this TAB times this would have to equal W times this. So that's going to be our 2 equations. And I just want to point out that it was redundant to get a unit vector. Alright, so I said unit vector, but I don't know. It's redundant to get a unit triangle. You know, we got a unit triangle, and it just visually represents kind of this scenario that we're maybe familiar with. But we didn't have to do that. Our percentage for this component was going to be x divided by 8. Let's go back to our original triangle. I mean, couldn't we say the percentage in this direction is just this distance divided by the hypotenuse? That's all we need to do. So we could say that component is going to be this x divided by 8. The vertical component was going to be this divided by 8. So that's all we had to do as well. And then this vertical component is going to be this divided by the hypotenuse. And so that's what we see right there. The horizontal component is going to be 10 minus x divided by that hypotenuse. So that's where, from the problem setup, is that if you do have geometry where the tension members are going to follow that geometry, then you can take those numbers at their face value and get the percentages of the tension just by dividing. So if I wanted the horizontal, take the horizontal distance divided by the hypotenuse. That's where it doesn't matter whether this is 10 or this is 100 and this is 80. It's still going to give you the same percentages in the vertical and horizontal directions. Alright, I've already solved this video once, maybe even twice. This was part 3, so that's all I wanted to show, was just to make sure it's more intuitive. That if you have some sort of geometry here, I can get the percentages of these tension members just by the geometry. Even though these numbers don't have anything to do with the numbers of the force, so we have like units of meters, and force is going to be in units of like pounds for weight. But we can use those percentages. So it's going to be this distance divided by the hypotenuse, and that just kind of shows you that that's going to be the percentage of this tension member in the horizontal direction, as well, and vice versa for the vertical direction. Alright, so sweet. Thanks for joining me on this one, and that's a video. Alright, hell yeah. So we're going to analyze this just for a second. I've been thinking about this quite a bit. It's just like, how do you get, this was the fast solution. How do you get to an answer and then just quit? You did all this work to get equations for, and it's just one scenario, but then cool, you have the position over here where this thing's at rest, and then what else do we know about it? Because the other thing that I was kind of fascinated with was just like, well, we know that the tension in this rope is the weight, is W. What's the tension in the other rope? Well, we have this tension in AB is this equation, and it's a multiple of W, so we can throw in, so let's do that. And so we have 8, 10 minus x divided by x divided by the square root of 8 squared plus 10 squared minus 20x. Alright, and we get 0.7 W. So that kind of gives us an idea that this side will have a weight, will have a tension of W, and that's why the pulley, that's what we determined from the pulley. This side will have a tension of 0.7. And this is and then we could figure out to see if the picture even looks representative. And no, the picture is, the weight is really more directly under point C than it is under point A. So there you go. So this tension over here is going to be a tension of W. This tension is going to be 0.7 W. Cool. And then, kind of to finish off, this got me thinking, because this is similar to a rock climbing anchor. Typically, when we have a weight that we're trying to hang, ideally, we would have 2 supports and then a rope attached to both ends. And if we're hanging a weight, both the tensions are going to be the same. So we have T there, and we have a weight down. Some of the forces says this W has to balance by, T plus T, or W is equal to 2T. Solve for what the tension is. Tension is going to be W divided by 2. So the tension is 1/2 the weight. So the tension in either of these is 1/2. Now, when rock climbing, the rule is about a 90-degree angle. If you do 90, you're fairly decent. But if your angle is wider than 90, if your angle is 120, so if this angle is 120 degrees, that means this would be 60 and this would be 60. But you can just imagine like a wide open angle of 120. Now if this is your anchor that you set up with carabiners and then a piece of webbing, and then you have your carabiners here, and then you're repelling or lowering, this is kind of like what you want to avoid. You wouldn't want anything worse than this, but you really even want to avoid 120 degrees, because we know that if we're hoisting a weight, whether we're rock climbing or doing anything, that the tension in both of these will be W. So this is kind of that special case, and it's kind of cool because if this angle is 60, where that W comes from is like, well, this angle is 30. And so the vertical component of a 30-degree angle, sun is shining on the sinin, so this is sine 30, that's going to be 0.5. So whatever this tension is, we said it was W, we're going to have W times 0.5 W, that's going to be the vertical component. Same thing over here. The vertical component is going to be 0.5 W. And then half the weight plus half the weight can support the total weight. So that's where we get that. And we might as well run the scenario, because I said climbers like a 90-degree angle. So we're going to have an angle of 45, an angle of 45. So this vertical component is going to be 0.7 W. It's going to be 0.7 times the tension, 0.7 times the tension, and then we have a weight. So we have weight is equal to 1.4 times the tension. Weight is the, and then so the tension is going to be the weight divided by 1.4. And that's going to be, the tension is going to be 0.7. I think it's just 0.707, the weight. Yeah, it's kind of fascinating how this is the square root of 2, and then and when you, what do you do? This is W divided by the square root of 2. Which you rationalize this. Yeah, it's so funny. You have W is divided by the square root. To rationalize this, you'll do this. And no, you'll get square root of 2 divided by 2. But yeah, that's the same thing as this. So yeah, it's so fascinating how 1 divided by the square root of 2. Yeah, this is tripping me out. We did this in our video. So you have 1 divided by the square root of 2. And if you rationalize this, you can divide both sides. You can divide by a factor of 1, and then you'll get the square root of 2 divided by 2. Cool. Now how do you go from square root of 2? Oh yeah, what am I even trying to say? No, yeah, it's the square root of 2 divided by 2. I don't know what I was thinking. But yeah, there's your equality. 1 divided by the square root of 2 is just the square root of 2 divided 1/2 the square root of 2. But yeah, so your tension in these members with a 45-degree angle will be 70% of the load. So whatever your weight is, you're hoisting a person, you're going to have 70% in that, 70% in that one, 70% in that one. Alright, so, but yeah, let's go back to this 120. It's kind of fascinating. This 120, though, only appears as if this tension is the same as that tension and is equal to this weight. So if the weight down is the weight here, and the tension in this one is W, the tension in this cable would also have to be W for 120 degrees. But you can imagine, like, hey, if this isn't W, we just said it was 0.7 W, well, then this angle is a little bit less. And so I think, yeah, that's fascinating. So I think what we're going to do to kind of finish up is let's solve for the angle. Since we did this problem not wanting to solve for any angles, well, now we're going to solve for this angle right here. So we have to sum the angles. We're going to take this angle and then add it to this angle. So this angle is going to be the, so yeah, this total angle is going to be, so this angle we're going to do, so this is how I do the angles. Hey, draw the sun is shining, and it's going to be, hey, on something we know, and we know the hypotenuse. So I'm going to take the inverse sine. Even though you took the inverse sine, I mean, you could just write out this step. Sine of this angle is going to be x divided by 8. And then you would say this angle is inverse sine of x divided by 8. So just know that even though you're taking the inverse sine, you're still putting the same ratio. So I'm going to take the angle right here is the inverse sine of x divided by 8. Alright, we're going to use that same logic to say this angle, sun is shining. We know the sine component. The hypotenuse is ridiculous. So we're going to just use this side. So we know the opposite and then an adjacent. So I'm going to say that's going to be inverse tangent of 10 minus x divided by the square root of x squared minus x squared. Cool. And this is going to be our angle. And we know what x is. So we can just literally put this into our calculator. So we have x divided by 8 plus inverse tangent 10 minus x divided by the square root of 8 squared minus x squared. Alright, booyah. So we get an angle of 110 degrees. And I think that's the most important thing about this problem is relating it to something, and we did. We related it to a rock climbing anchor. Anytime we have a load and one of our tensions trying to hoist that load is going to be the same amount as that load, then we're kind of thinking this scenario. where it's like, hey, this tension is the same as that tension is the same as the load. Now, this is going to be a little bit less. That means we're not going to have that 120 degree angle. If for whatever reason this was more like a 1.4 W, well then our angle would have to be increased. So it's just kind of fascinating that we can go back and choose different lengths for this rope. So one scenario that I did is just like, well, let's intuit, if this is 10 meters and we have a 120 degree angle, that's the easiest way to do is just split it right down the middle. So this is 5, this is 5, this is 120. Now, so this is 60. And again, using my axiom of like, if you have a right triangle and you know two things about it, you know everything about it. So I know an angle and a side, I know everything. I can get this hypotenuse right there. And that's the length. I really want to know that length when we have this scenario where we have equal weight. And so let's use that thing. If we want to know the hypotenuse and we know this angle and the sun is shining, so we know the kind of we know that the sine of 60, or how do we do this? I would say you take this. Yeah, we're going to take this length, but we need it to be bigger, right? So we're going to divide by the sine of 60. Sine of 60 is a smaller number, and because this is the angle we're using, and this is the sine component of that angle, that's how I can get here faster. It's way easier if you know the hypotenuse. You know the hypotenuse and you know an angle. I can get to the sine component. Just take the larger angle and multiply it by the sine of 60, and that's going to be that component. But it's interesting when you have one of the shorter components, how do you get the hypotenuse, which is a bigger number? You take that component and you divide it by that fraction. Sines and cosines are fractions. So there you go. So we got 5 divided by sine 60. Okay, and we get 5.77 meters. So if this length is 5.77 meters, this weight will be perfectly in the center and we'll have that 120 degree angle. All right, booyah. And I should probably do one more, you know what I mean? Because we said if this length was longer, that the angle was less than 120, and this tension had less than the weight. So I'm just curious, if we make this this length shorter, you know, how will that change the problem? All right, and before we jump into solving, you know, another problem, is like, you know, can we intuit this? Because here's a scenario where, hey, let's say we just have a very short rope. So this is kind of taking the problem to the extreme. So I mean, less than a foot even, and we're going to hang that weight right here. But we still have this connected way over here to this pulley, and we have a weight that's pulling. So it is pulling in this direction. So we have two things going on here. Let's say we don't have this part of the equation. It's literally directly hanging under this. So from that scenario right there, the tension in that cord is W. You know what I mean? From that single scenario. But then the second we actually start tugging on it from this direction, this angle definitely changes. Even if it just changes slightly, and then we're gonna see what happens. Because if this tension now is like at an angle like that, only the vertical component can be useful in hoisting that. And hopefully we drew our problem good enough where this is so short that all this is literally doing is pulling sideways. Just from an extreme, this sideways pull is absolute. We're just going to say is absolutely not help hoist this thing up. So now we have a scenario where we have we're trying to we're trying to lift something, but at an angle like that. So if this is how we have to lift this, and then you might have to get kind of creative. Like, how would you actually lift something like that? Well, let's say we do have a wall here, and we have some wheels, and there's our mass, and you're still pulling at that angle. So to lift this up at this angle, you're going to have to put more weight. That was the whole thing I was getting at. Is like that's, you know, you're kind of interested, like first is like, well, is the weight going to be less or more? In this scenario where we had no sideways pull, the tension was going to be just the weight of this. So this had a weight, and the tension in that rope was going to equal that weight. The second we pull at sideways, we're going to say this is directly sideways due to geometry, because we're making this really short. And so we're explaining what would happen pictorially, even though you could go through the equations and also come to the same conclusion. All right, so in this scenario, this has to be more tension. So the tension has to be greater than W. So the tension is going to be like maybe 1.2 W. I don't know, like 1.4 W. But there you go. So we know in that scenario where this cable is shorter, the tension is going to be greater. And I would just suspect is if the tension, I mean, if this length was less than 5.7 meters, I bet the tension in this cable is going to be more than the weight. But I'm not quite positive on that. Just because at this perfect angle, like it's a little more subtle. So if we have this 10, this is kind of our halfway point. If we say we kind of shorten this cable up just a little bit, that means, like, well, one thing is that this is going to be longer. And if this is longer, it's going to pull more at a horizontal angle. And so this efficient angle of halfway gets worse. And I think we still have the same setup. So that would be kind of fascinating. So so instead of doing a bunch of calculations, if you were just curious on figuring out this, I would just say, hey, when x is 5.7, find the tensions in the cables. Oh, my bad. I said that wrong. I said x is 5.7. No, what I meant to say is that this length, the length of AB, would be 5.7. If we put this section of rope to be 5.7, then we'll probably have that scenario where this tension is going to be greater. And so, all right, hell yeah. And I don't want to do too much more work, but we already did this, once when our length was 8, and we want this length to be 5.7. And this is kind of fascinating. I'm trying to get better at like just making these into equations with variables. I don't want to do that one yet for this problem. But hey, this would be 5.7. That means that this 8 would be 5.7. Everything really kind of stays the same. And so what we're interested in is the tension of AB. So this just becomes 5.7, 5.7. And I don't think anything else changes. So let's try that out just to see. So we're going to say 5.7. Oh, well, definitely this x value changes. So, yeah, that's a bummer. So we would have to run through the whole problem and find the new value of x. Yeah, I think we should do that. All right, hell yeah. So let's do it. So we're going to say this is 5.7. And we want to find that value of x. And let's try to do it as fast as possible. So this is going to be x, 10 minus x. This is going to be the square root of 5.7 squared minus x squared. Cool. So a lot of things don't change. 10 minus x squared is going to be 10 squared minus 20x plus x squared. Cool. So then when we take the square root of this, it's going to be this squared. Square root just goes away. And we got 5.7 squared. We have a negative x squared. We're going to add it to those, so those go away. Plus 10 squared minus 20x. All right, so that's that hypotenuse. Cool. We're going to sum the forces in the y. That's going to be, I guess let's throw this, we're going to put this all equal to weight. So we're going to say the vertical component is going to be the square, 5.7 squared minus x squared divided by 5.7. This is going to be the tension AB. Plus, now the vertical component of this is going to be that same thing, 5.7 squared minus x squared divided by, but this hypotenuse, 5.7 squared plus 10 squared minus 20x. And that's going to be the tension in this rope is going to be the weight. Cool. In the x direction, we're going to have the horizontal component. That's going to be x divided by 5.7 of tension AB is equal to the horizontal component over here, 10 minus x divided by the square root. Since I'm going to write this 1,000 times, it's just this times the weight. I'm just going to solve for TAB. That's going to be 5.7, 10 minus x divided by x. And we'll write this in a second. And then I'm going to substitute up here. So I'm going to have, and this is, we got a w here. So we just took those two terms to the other side. 5.7 went there, x went downstairs. Now we're going to come back here with this term, 5.7 squared minus x squared divided by 5.7. We have this 5.7 times 10 minus x. We have this downstairs. This is 5.7 squared plus 10 squared minus 20x. So that's this term. We just put this, and then we put this right into there. We do get a w. All right, now we're going to add that. And, cool. Yeah, we'll do it. 5.7 squared minus x squared. Yeah, that's just the bummer with doing these, is like how many times do you have to write the same thing? Okay, so that's going to equal, and I'm sorry I didn't even do it. So this plus this equals w. So yeah, in the y, the vertical components have to equal the weight down. And now we can do that. This 5.7, that kind of goes away. And then we need an x down here, we need an x up top. If we factor this out, we're going to have a 10 minus x plus x. So we're just going to have a 10, this term, divided by x, that term, is equal to 1. So now we're going to get this upstairs. So let's just do that right here. We're going to have x, that term. Sweet. So again, this smaller term is this, bigger term is that. Now we're going to have a 10 squared factored into this one. So we're going to have 10 squared, 5.7 squared minus x squared. We do have a square root, but that's going to go away. Is equal to, we're going to factor this in, x squared, and that's going to be 5.7 squared plus 10 squared minus 20x. And again, you don't have to get this too far. I mean, like right here we're done. And we just get rid of the square root. So now we can go right to our calculator and then just put this in. I'm going to do this side first. So we're going to have x squared, 5.7 squared plus 10 squared minus 20x. And it's fascinating to do this with just changing one variable. And you're like, whoa, a lot of things didn't change. Like this was just totally just a function of that length. You know, there was nothing about 8 that made this term or this term different. And so I think that's very useful. Everyone just says, hey, like, you know, you should do, use variables right from the start. I disagree. I think you should use numbers that you're familiar with, extreme examples that you're way familiar with, and then slowly start building more complexity. And then also don't be afraid to do a problem like, 4 different ways or more. And, just throwing in another value and going through the whole process, you're less likely to make mistakes. All right. And so let's do it. So we have minus 10 squared, 5.7 squared, minus x squared. And yeah, we'll see if we made any mistakes. So we took this and subtracted this, so we basically got this, you know, these two, everything's equal to 0, where x, the value of x, is going to make this side 0. So that's kind of how we solve for that. So zoom 6, we're going to see where it crosses. All right, let's get our 0 value. And sweet, so we have x is 4.923, and so we have that in our calculator. What we want to do is, what we were most interested in was just solving for the tension. So we have 5.7, 10 minus x, divided by x, divided by the square root of this thing. 5.7 squared plus 10 squared minus 20x. And yes, it's a little bit bigger. Oh, and that was perfect. We thought, yeah, that was so fascinating, because 5.77, it was even Steven, weight and weight. But we figured if it was like if this length was 5.7, you know, not 5.77, that this weight would be more. It would be greater than one factor, and we get a 1.007 weight. So that's also cool, where you can, you know, kind of intuit like something and then go back and put the equations to it. So hell yeah, I'm very satisfied with this video now, especially getting to show you something about rock climbing, how that angle is 120. And yeah, so for that scenario, we're going to have an angle of 120. I really want to do more with this, but I think I'm done with this video. I think what I'm going to save for another video is to get this length. So you would say that this would be L, and then this would be KL. So in this situation where this is 10 and this is 8, this would be L is 10. And then you would have 10 times 0.8 is 8. So your factor, what would you call that? Your kind of proportion of this total length for this length is that K value. So if you had 80%, so that K is 0.8, that means 80% of this total length is that equal to this length. And it'd just be fascinating to get an equation where then you could very quickly, well, and this is a bummer because there's no real good way to besides using a solver, or you know, or doing harder methods to solve a cubic. There's just no easier way. You can't get that's the bummer. You can't just say here's x. That's the cool thing about the quadratic formula, is you literally you can take something, if it's a quadratic, you can say, hey, this value of x, inputting anything else, inputting this L, L, and KL, you could just get one solid equation. But that's where this one, you would just run into issues. You could get down to like an equation that's ready to be solved in a solver. But that's as good as that you could get. And then you could change those variables. So you could change those variables, solve for x, and then use that value to solve for the other things. Yeah, I think I'm kind of done. I'm just curious, if this length was 1 foot, what would the angle be? You know what I mean? I can't think of that right now. And the only thing that I can think is that if this length is super short, like that rope is super short, and then you're pulling dead sideways, what happens when you pull dead sideways on that? I honestly, I'm confused on that. Whereas just like, is this going to have an angle that's similar to 120? I don't think so. I think this angle is going to approach 90. I think that angle is going to stay the same. If you had, like the tiniest bit of rope with this weight, and then you come in and pull right on this point, but this direction, dead sideways, with a force of W, as it goes around the... I don't know. I need to visualize that one. I don't know if I'm going to be done with this video yet. Alright, hell yeah, we're going to do that. So we're just going to say this length is 0.1 meter. I am incredibly curious. And we can just use the same geometry. So we're going to have, and we can do it quite a bit faster. So 0.1 squared minus, this is x, 10 minus x. Minus x squared. Square root that. This is going to be 10 squared minus 20x plus x squared. So our hypotenuse is going to be 0.1 squared plus 10 squared minus 20x. Cool. The vertical components are going to be, and since we already have these now we're just good to go. This one is going to be the smaller, and this one is going to be the larger. So in the y direction, we're going to have this tension AB, the vertical component. Vertical component is going to be this length divided by 0.1, tension AB. Cool. Plus, see, and I think this is a good skill, because that's like 3 strokes of the pen, and you're understanding the concept of the, the second you have to write too many things, the concept kind of goes away. Okay, now the tension of this. It's going to be this component divided by this component, the longer one, and that's going to be W. Alright, and then, so those are the 2 vertical components. That has to equal W. Horizontal, we're going to have x divided by 0.1, tension AB, is equal to 10 divided by x divided by the hypotenuse, which is this. Cool. Alright, and then that's W. So we can say that the tension AB is going to be 0.1, 10 minus x, divided by x, that, W. Sweet. So now we can put this into here. So we're going to have the smaller one divided by 0.1. We're going to have 0.1, 10 minus x, x, and then the bigger one. So the 0.1s cancel. We're going to have a W here. Forgot about that. Plus the smaller one, the bigger one, W is equal to W. Okay, so we get 1. These all cancel. And now we need to have the denominators the same. Booyah, now we can add. We can factor out this, and we're adding 10 minus x plus x. So we're just going to have 10. 10 times this. That's it. Bottom is going to be x and then the bigger one. Cool, that's going to equal 1, which essentially is 10 smaller one, x the bigger one. Cool, so now we just factor in. Yes, it's so fascinating how it's like your mind can't do all this in one step, but it's just fascinating how once you get to the new step, you're like, yeah, no duh, why didn't I just see that? But yeah, this is kind of my method of just why not do a problem 4 or 5 different ways? Even if you do it the same exact way, it's going to help you catch errors for sure. Okay, so we're going to have 10 squared, and then we're going to factor, I'm just going to say this, the smaller one is equal to x squared and then the bigger one. Cool. And so now we're ready to go though. So we put it into our calculator. We're going to have 0 is negative. So 0, let's do this. 0 is this one, x squared, the bigger one, minus 10 squared, the smaller one. Okay, so now let's get this equation and solve for x. So we have x squared times this bigger one, 0.1 squared plus 10 squared minus 20x, minus 10 squared, and then the smaller one is 0.1 squared minus x squared. And we can even go to our calculator and see it's oh yeah, no duh, this just changed to 0.1. So we're getting closer to be like, whoa, we even have an equation. All we have to do is just change that length. That's it. You know what I mean? So that's so fascinating, that whole process. That was the only thing that we needed to change, was just this to 0.1. I'm just going to double check to make sure I did that right. And, all right, graph it up. Oh, I kind of want to see what's going on here, so we're going to, yeah, because it's happening all at once just right here. Okay, there we go. So we're going to get our 0 value. Whoops. Left bound, right bound. Okay, so we have an x of 0.07 meters. And our length is 0.1 meter. Oh, and that is what I was, well, I don't know if I was assuming. I thought that's what I was assuming. Like it was going to pull at a 45-degree angle. Is that kind of what that says? That angle is going to be 45, and so what does that mean for the total angle? So we're going to go back and figure that out. So this angle, the total angle of this whole thing is going to be this one, and we know the sine part, so we have inverse sine of x divided by 0.1 plus inverse tangent, so this one is going to be 10 minus x divided by the square root of 0.1 squared minus x squared. Alright, let's do it. So we have inverse sine x divided by 0.1 plus inverse tangent 10 minus x divided by the square root of 0.1 squared minus x squared. Okay, and we get an angle, I don't even know if this is right, 134.79. Okay, so this was good, because my intuition was totally off. And it's because this thing is just going to pull sideways until this component, the vertical component, actually, I don't even know. But yeah, that's fascinating that it's more than 120 degrees. Okay, and I should have intuited that, because when this length is longer than 5.77, which would make a nice 120 degrees, this angle, back to... Let's see, do I even have it? Alright, hell yeah. So back to this angle was less than 120. So the longer this is going to be, the more that this angle is going to approach 90. And okay, so that makes sense, because there's a scenario where if this rope is 10 meters long, whoa, that's really tripping me out, because it has to be in an ideal situation. If this rope is 10 meters long, it's always like when it's swung out down here, it's always going to have a weight of 1 on it, and this one's not going to be doing much at all. So I think equilibrium has to bring it up here, and it has to, if this rope is 10 meters, it literally, x has to be 10. Even though, like, if you make this rope longer than 10 meters, where it's just slack, I mean, basically, if you just have both of these weights going around this pulley, they're at a stable equilibrium. Where as long as both masses are at rest, you know, they're just chill. But it's Alright, got a new battery in. Alright, so I guess what I was saying is that if this rope is really long and it's directly, and this part is slack, these two weights will just be, you know, stable. But the only way you're going to have an unstable equilibrium is if you bring this one to where there is tension in this rope. And to put tension in the rope, you just move this weight out even if this is, so let's draw that, even if this is just really long, more than 10 meters, but that weight is right there, you're still going to have a component, you know, this is going to have a tension W, and you're going to have a component that way, and basically it's going to be all this way. You know what I mean? You have a weight that way. And the only way to, see, yeah, this is kind of fascinating with vectors, is so you will have a component of this in this direction, which you have to balance to make this thing not move. You're going to have to put a small component, that same small component in this direction. And if you do that, then this has to get tension. And if this gets tension, it's also going to have a vertical component. I think that spells it out. Is that this, you could imagine that this vertical component is almost 100%. Cool. But it does have a, and this is what happens all the time when you, this is why I do like a 30-degree triangle. That's pretty close to 30. But it'll say that this is half. The hypotenuse, hey, this dimension is half. I like to estimate that this length, it's 0.866, but it's approximately 1. You know, and then let's take this down to a 15-degree angle, where this component is going to be 0.25. So we'd split that up 4 ways, and you can see that, yeah, this length is about that length. This becomes like 0.94, or, you know, now this component is 1. It's not quite, but that's what we have here, is that this angle is so shallow that the vertical component, you know, it might be 0.999. You know what I mean? We could just say that it's 1, but the horizontal component is going to be like a quarter of that. So even just like right here, sorry we're getting so, I mean, I got more paper. So we're going to take this, going to draw, you know, we're going to draw it up. So here's our hypotenuse. You know, how many times do we get to divvy this up? 1. I bet you we divvy this up 8 times. Cool. Well, you know, I mean, that's close enough. But if we divvied this up 8, this is going to be 0.125. So this is about 0.125. So if this hypotenuse is a unit length of 1, this becomes like 0.125. And it's a little bit more. So maybe this is 0.15. Just kind of like, well, not like we were doing. But anyway, so we have 15%. Now, we can basically say, and here's our weight, and then we have this angle over here, which is visibly more. I mean, and we're to scale. So if we have a component, this has a weight of 1, basically 1, or W, then it has a component this way of 0.15 W. Cool. And then so we have to have a component this way of 0.15 W. Now if this angle is a 45-degree angle, hey, we're going to have 0.15 W this way and a 0.15 W that way. But we don't have that. So we can draw similar triangles here, and this is kind of interesting. This is kind of like the geometric representation. So we're saying that this is 0.15. Oh yeah, this is tripping me out, because it's just like, well, shouldn't we have a smaller triangle here? Well, yeah, I mean, if we have similar triangles where both these angles are the same, where that angle's that angle, and this is that 0.15 component, and this is 0.15, well, yeah, then you have nice and balanced, but we don't have that. So we're still picking up 0.15 W in this section, and just by similar triangles. Like if this, like you can just, even though that these are different sizes, you know, we can basically say, hey, this size triangle is still representative of all three of these sides. Just like, coming back here, this 0.15 W right there was representative of also this horizontal component. So if we started chopping this up at 0.15, so 1 divided by 0.15, we would divide this thing up about 6-7 times. And we go 1, 2, 3, 4, 5, 6. So we have 7 chunks, and they're all 0.15 W. So we could say this vertical component is basically, 0.99 W. This hypotenuse is W, and that checks out. So now we do the same thing here. Even though we're looking at a different triangle, I'm still saying that the number on this portion of the triangle is 0.15. So just like we went back here and said, hey, if this hypotenuse is 1, what is this dimension? And we did that. So now we're doing it in the reverse. If we're saying this dimension is 0.15, well, I think I can divvy this thing up about 3 times. And then, so look at that. So, if this is 0.15, I can't even divvy this thing up 3 times. I could divvy this thing up twice. Look at that. So if I divvy this thing up, this hypotenuse, twice, I basically get that same length. So then what I know is that this hypotenuse has 0.3 W. So that's wild. And now and then I could say that, maybe a little bit, maybe even a little bit more. Because if I divvy this up twice, those look about the same. This might be like 0.35 W. All right, so let's go with that. That's going to be more accurate. But now what happens is these things are balanced. This weight is going to have 0.5 W that way and 0.5 W that way. It has a weight of W down. We're pulling up with a weight of almost W, basically equivalent to W. But now we're also pulling up. This hypotenuse is now we're pulling up with this tension. Sorry, I need to say this is 0.3 W. So there you go. So my vertical component up over here is 0.3 W. So let's do this again. So this point right here is down with W. Up, the vertical component of this is, 0.99 W. And then plus this is 0.3 W. So we basically have 1 W plus 0.3 Ws. And we get 1.3. So if we have a weight that has a weight of W, but we're putting a force of 1.3 W, this is not in balance. This is not in equilibrium. And so we've just shown that if we make this rope really long and then we offset this weight from the horizontal, then this will start to climb. And that's really trippy, because why is it trippy? Well, no, it's trippy just because where you're going to get balanced, this thing is going to balance out. So let's draw one more photo. I guess we don't have any more sheets of paper. But this thing is going to balance out. Like this rope is really long, but the second this length of rope, gets to here, hey, this rope is going to go slack. Right here is going to be slack. And so at this point right here, now you're in a stable equilibrium. Is that this tension is W, the weight is W, and this thing is not moving up and down. So I think that finally, man, these problems are tricky, but there's so many things like this that you're just you talk your way through. And you can also go back to the equations. I could have set this length to be hella, and then I would see where the stable equilibrium is. And what I would find is I would find stable equilibrium when x, this dimension, is equal to 10. So if I say the length is 10, I'm also going to find a stable equilibrium point when that, yeah, that's fascinating to me. When basically this length is 10, and it is going to go slack because the weight is held right here, and then this weight is held right there. And then so, yeah, at 10 meters, this rope technically has zero tension in it. It goes slack. Just like if it was 10.1 meters long, and this distance was only 10 meters long, 10.1 meters, then it for sure would go slack at some point, and then go up and over the pulley. And so when this is 10 meters, not only does it go slack, but I guess I should say if this is less than 10, so in the situation where this rope is just slightly less than 10 meters, it's going to be pretty much vertical, but now it's going to be slightly down. And then you can see that, you know, if we have a vertical rope, the only way it can move is in a kind of a circular path. So straight down is basically perpendicular to the pulley. So then the angle between the rope and the pulley right here, this angle approaches 90 degrees. So as this rope approaches 10 meters, that angle approaches 90 degrees. So in our problem, where we had 8 meters, which is pretty long, you know, it's getting out there. And so to show you the picture again. All right, hell yeah, and I think we're going to be done. But yeah, so if this is 8 and this total is 10, yeah, this angle becomes less than 120. So this actually becomes 110. I don't know if I actually solved for this. Hopefully I did, but I don't know if I did. But yes, and as this length, this 8 goes to 9 to 9.5 to 9.9 meters, this angle approaches 90 degrees. All right. So that kind of is the full rundown on this problem. It's very interesting. And I like it. Anytime you get a starred problem, and that was where the commenter was just like, hey, do you have any harder statics, trigonometry problems? Sometimes he was looking through his book, or they didn't really have textbooks. They just had, you know, handouts. And so you're just like, well, how do you get harder problems? Nobody wants like too hard. But I thought this was like a perfect, hey, you know, it involves trigonometry, and you can do it without solving for angles. You know, maybe at the end you want to solve for this angle, but you can do the whole problem using triangles and proportions between the opposite and adjacent sides and their proportions to the hypotenuse. So that's what we did today. And man, all right, I'm excited about this one. Thanks for joining me, and that's a video.